Sometimes we're given a quadratic equation. Other times we have to find it ourselves. How do we find it? Well, if we have the roots, then we have the family of the quadratic equation or quadratic function, because we're going to be plotting one variable against another. So say we have, oh, these 2 points, it must pass through these. Well, we can go like this, we can go like this, but regardless, we have constraints, right? So the formula is going to inevitably look like this. Now, a cannot be 0, otherwise our function would be flat line, y equals 0. Yeah, no, that's not quadratic anymore. So a is not 0, and a is a real number. So from negative infinity to positive infinity. This gives us zeros, so fx equals 0 at x equals m and x equals n. Now example 1. Suppose we need to find a family of quadratic equations given the zeros. Well, hey, when does this equal 0? Well, when x plus 1 equals 0. And, well, say we remove 5 from this. So x minus 5 equals 0, and lo and behold, this fx would be 0. F of 5 is 0, f of negative 1 is 0. This is a sketch of some members of this family. Now here, we see a few different members. Let's think about what they might be. Well, suppose we set a equals to 1. That means it would open up. And what would the lowest point it would reach be? Well, it would always have to be at x equals 2, because that's the average between negative 1 and 5. We know that parabolas are symmetrical. So, x equals 2, and if we want x plus 1 times x minus 5, so in other words, 2 plus 1, 3, times x minus 5, that's negative 3. So negative 3 times positive 3 is negative 9. Lo and behold, if a was 1, that would be over here. So this is y equals x plus 1, x minus 5. Now this one here, it actually doesn't quite reach the negative 1 line. And I seem to remember as having entered it as y equals 0.1 times x plus 1, x minus 5. Now what about this inverted one? Well, hey, here it's 4.5 at its highest point. So you mirror it and it would be 9. So we demote that by half and we get negative 0.5 x plus 1 x minus 5. So even though this question didn't actually require us to label these different functions on the graph, it's often a good idea to do so if you, well, okay, if it's not asked of you, really it's a bit of a personal choice, but if you think it might come in useful for, say, learning how to identify functions, or even thinking, mentally reviewing about how to identify functions, then it's a good idea. Assuming you have time, of course. On, say, a contest, if you're not asked to do something, usually don't bother. I mean, unless it could potentially lead to a solution for another part of the problem, but that's another story. That's basically being asked to do something, right? Okay. Now, suppose we have a family of functions with zeros at 2 and 6. So 2 and 6 as graphed here. What can we do? Well, we know equals a times at x equals 2. This bracket is going to end up being 0. So it's going to be x minus 2. And at x equals 6, this bracket is going to be 0, so x minus 6. So here, what we might have is, well, at 4, we have x minus 2, 2, and x minus 6, so negative 2. So this red line here, 2 times negative 2 times a is negative 4. Obviously, a must be 1. Well, actually, this should probably be an arrow to indicate that red is fx equals x minus 2, x minus 6. And then green is f of x equals, here it goes down to negative 12. We know that it goes to negative 4 when a is equal to 1. So to go to negative 12, we would have to scale it up by 3 times. 3 times x minus 2 times x minus 6. And the blue, well, okay, we can flip this over. And it seems to be a little bit under half, so this looks like, most likely, it should be f of x equals negative 0.1 and times x equals minus 2 and x minus 6. Well, this is a family, and here are some of the possibilities we can have in this family. Remember that we always have infinitely many in a family of quadratic functions. Why? Well, it's because a goes from negative infinity to positive infinity. Thus, infinite number. Okay, C. 9 is the x-intercept of a family of quadratic equations. What does this do? Well, we know that we can have 2 zeros, we can have 1 zero, so in other words, 2 identical zeros, or we can have no zeros. So fx equals x minus 9 squared times a. So when x is equal to 9, this is 0. We have 2 identical zeros, or 1 0 as most people would call it. In this case, in this red line's case, we go 1 grid over and we end up 1 grid up. 2 grids over, 4 grids up. This is most likely f of x equals x minus 9 squared. And for this one, we go 3 grids over and we go almost 1 grid up. And we go 4 grids over and we go a little bit over 1.5 grids up. That means this is most likely f of x equals 0.1 x minus 9 squared. Okay. What about this one down here? Well, we can see, 2 grids over, a little bit over a grid down. And what about here? 3 grids over, and something like a bit over 2.5 grids down. I happen to remember that I wrote negative 0.3 x minus 9 squared. However, unless you actually wrote that yourself, don't be so certain. If you can't figure out what to label it, don't label it. Why? You don't want to look back at the diagram later and be, say, misguided by a misestimate from earlier, right? Now, example 2. We have to determine the exact equation of a quadratic function. Express the answer in standard form. What is standard form again? Ax squared plus bx plus c equals 0. Yes? Or equals f of x, depending on the case. So what we're looking at is zeros at x equals -3 and x equals 2. This passes the point 3, 4. So we have fx equals a x plus 3, so this makes this a 0, times x minus 2, which makes x equals 2 a 0. So this passes the point 3, 4. Now, what this does is that we know f3 is equal to 4. This happens to mean that a, x plus 3, x minus 2 equals 4. So a 3 plus 3 times 3 minus 2 equals 4. Thus, a times 6 times 1 is equal to 4. A equals 4 over 6. So, this is 2/3. Thus, f of x is equal to 2/3 x plus 3 x minus 2. This is equal to 2/3 of x squared plus 3x minus 2x is plus x and minus 6. 2/3 x squared plus 2/3 x minus 4. A lot of teachers seem to like it when you reiterate exactly what you are getting by putting, say, y equals, even if up there it was just y equals, 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 equals. So if your teacher likes this, go with it. Now, the zeros 2 plus root 3 and 2 minus root 3 contains 0.59. So this is a little bit more complicated. Here we have f of x is equal to a x minus 2 minus root 3 times x minus 2 plus root 3. Here, what we're actually looking at is this. X minus 2 minus root 3 x minus 2 plus root 3. So this is a plus b times a minus b equals a squared minus b squared. So what do we have here? We have x minus 2 squared minus root 3 squared, which gives us a times x squared plus 4 minus 3. So equals a times x squared minus 4x plus 1. So we know that f of 5 equals 9. So we have a 5 squared minus 4 times 5 plus 1 equals 9. Now, depending on region, you might have to upgrade this to square brackets, but some areas are fine with nested round brackets. So there are many curiosities in terms of math rules and regulations. For example, Excel documents or other spreadsheets use many nested round brackets of varying colors. They actually display the text in different colors so that you can actually see which is curious, yes? So 5 squared, 25 minus 20 plus 1 plus 1 a equals 9. So 25 minus 20 is 5 plus 1 is 6. 6a equals 9. A equals 3 over 2 because 9 divided by 6 is 3 over 2. So what we have in the end is f of x equals 3 over 2 x squared minus 4x plus 1. Three over 2 x squared minus 4x plus 1. 3 over 2 x squared minus 6x plus 3 over 2. So this is what we get in standard form, and to satisfy teachers who might want to write that in front. Now, of course, we omit the statement for time, and in this case space as well. So we have example 3. A soccer ball is kicked on flat horizontal ground. Okay, after traveling 28 meters horizontally, it passes just over a 6-meter tall wall and hits the ground 32 meters from where it was kicked. Wow, that's a pretty long kick given it passes through a wall that tall. Now we're presuming that this is a parabolic trajectory, so that there's no air resistance. Let the point the ball was kicked from be the origin. Let the ground be the x-axis. Determine the quadratic function that can be used to model the path of the ball. So we have zeros, x equals 0, and x equals 32. Now this passes through a point where it's 28 meters that way and 6 meters up. By just passes, we assume it's passing through that point. Now I do realize this is not a realistic assumption because real walls have thickness. They don't come up to a knife blade. And also the ball actually has volume. It's not just a dot in space with 0 volume. So the bottom side of the ball should, even if it was a knife, should still scrape against the wall. But hey, we are using an abstraction here. So f of x equals, well, x equals 0. That means we just have a x minus 0, or, well, just x term. And x minus 32. So through 28, 6, that means f of 28, 6. So we have a times 28 times 28 minus 32 equals 6. 28 minus 32 is negative 4. So a times 28 times negative 4 is equal to 6. 28 times negative 4 comes out to 112a, and this is equal to 6. So a is equal to negative 6 over 112. So what we're looking at for modeling the path of this ball is f of x is equal to negative 6 over 112 times x and x minus 32. So yes, okay, we're supposed to determine the quadratic functions. There are no instructions about what form we have to put this in, which means we're going to put this in f of x equals negative 6 over 112 x times x minus 32 is the desired function. Okay, now we should determine the maximum height of the ball. We know that it was between x and x minus 32 in terms of the lateral distance it reached. Well, okay, where in between? Well, because parabolas are symmetrical, it should be midway in between. So at x equals 16. Now, why is it that having a negative coefficient up there made sense? Because this opens downward, this parabola. And between x equals 0 and x equals 32, those things, when you multiply them together, the x and the x minus 32 terms, one of them is positive, one of them is negative. Thus, we end up getting a negative number multiplied by the negative coefficient gives us positive for y value, or fx. So f of x equals negative 6 over 112. I mean, we could also write this as 3 over 56. And actually, quite a number of teachers might prefer we do that because lowest fractions. But hey, it doesn't make a difference if your teacher doesn't have a problem with it. Why? Because we have calculators. So, highest point at x equals 16. So f of 16 is equal to negative 3 over 56 times 16 and 16 minus 32. The biggest rectangle that you can get is a square. So one of the ways to make sure that you have it right when you have it in factor form is that this number and this number end up being the same or the same and of opposite sides. So in other words, you get a square or a negative square. We could give this neatly as negative of 16 squared times negative 3 over 56, but we're not. Why? Cancel this down to a 7 and this down to a 2. And we get negative 3 over 7 times 2 times negative 16. So this is 32 times 3, so 96 over 7 meters. The ball at most 96 over 7 meters up. Now, honestly, we should probably have put it up here that fx is height in meters, x is horizontal, distance in meters up here as well. But hey, at least we recognize this and went back and changed it up. Now, how far has the ball traveled horizontally to reach the maximum height? Well, because its parabola is symmetric, the ball travels horizontally a distance of, well, we know that it started at 0 and landed at 32 meters. So it has to be 16 meters, halfway. To reach the max height. All right. So here we restate the problem to make things a little bit simpler on us. We need to use the vertex of the parabola as the origin. We figured out earlier that it was fx equals negative 3 over 56 times x, well, x here, x minus 32. So if we use the vertex of the parabola as the origin, what happens instead? First of all, this here, this negative 3 over 56, that doesn't change. What we could do is move this vertically, and then, well, we could move it horizontally by giving both of these some modifications, but why would we? We know that the vertex is now set to be 0, 0. And we know that the general multiplier, the coefficient of the first term, so the leading coefficient, is the same as long as the parabola has the same shape. What does that do for us? This is what it does for us because we only have one root and it is at the origin. What does that tell us? We're dealing with ax squared. And a, the leading coefficient, is the same as long as the parabola's shape stays the same. So yeah, here we go. Alright, example 4. Determine the equation for a quadratic function with zeros at this. What is this? Oh hey! X equals negative b plus minus root of... Note that it says a quadratic function, not the quadratic function. So we don't need to consider, hey wait, does the 2a cancel out with the b to get negative 1 over 5? We don't need to consider that stuff. What we do need to consider is b squared minus 4ac. So this is b can be 1, a can be 5 over 2, and we would need to have 11 equals b squared minus 4ac, so equals 1 squared minus 4 times 5 over 2 c. So this is 11. Now that means that first of all we cancel this part out, 2. So we would have 10 equals negative 10c, because 2 times 5 is 10. And we move this 1 over to get 11 minus 1 equals 10. So c is equal to negative 1. Thus, we could have f of x equals 5 over 2x squared plus x, ax squared plus bx plus c. Now, plus c would be minus 1. It only said determine the equation for a quadratic function with zeros at this. It didn't say a family of. That would make it a little bit more complex, but for now we leave it at this. Is a function with these zeros. Zeros given above. Okay. Well, that's it for this section. Hopefully we are now okay with finding quadratic equations given the roots. I know this is review. Some textbooks seem to be full of a lot of it. But hopefully this is still a useful review, just in case. So we'll see each other again then, next section.